Just like rivers flow across the landscape, submarine canyons flow across the bottom of the oceans, incising the seafloor and creating spectacular morphologies. Submarine canyons are large and deep submarine valleys. They provide one of the main conduits through which sediment, nutrients and pollutants are distributed from the land and coastal waters to the deep ocean. Submarine canyons also have a powerful influence on the nature and distribution of seafloor biological systems. Due to their relevance and widespread occurrence, submarine canyons are now extensively researched, particularly as technology advances have allowed scientists to explore these otherwise inaccessible and remote environments. Many submarine canyons are thought to have formed when sea levels were lower than today, and they were connected to major terrestrial river systems, such as during the previous ice ages. Sea level rise after the ice ages disconnected the canyons from the rivers, and as a result, many submarine canyons became inactive. Some canyons, however, did remain active. Recent surveys have also shown that numerous submarine canyons have never been connected to a major terrestrial river system or to the coast. Scientists still find it difficult to explain all of this. CUMECS is an oceanographic expedition that will try to address these intriguing questions. The CUMECS expedition investigated a poorly explored region of the Mediterranean Sea, known as the Malta Escarpment. The Malta Escarpment consists of a 3-kilometre high steppe, located to the east of Malta and to the southeast of Sicily, which separates the western and eastern Mediterranean basins. This region is important because it is a gateway for the exchange of water masses of different densities between these two basins. Existing poor quality seafloor maps from the Malta Escarpment show that this feature is incised by numerous submarine canyons, despite the fact that the slope has been isolated from the inputs of fluvial and coastal sediments for many thousands of years. The Malta Escarpment thus constitutes an excellent natural laboratory to study submarine canyon formation in regions of low sediment input.
The objective of the CUMECS research cruise is to first explore the Malta Escarpment, which is one of the least explored regions in the central Mediterranean Sea, and then to focus on the formation of submarine canyons that have never been connected to either a terrestrial or a coastal sediment source, and also to understand the kind of biota and habitats that characterize this type of canyons. The idea for CUMECS started about a year ago, when Eggy and I found out about this project called Eurofleets, which is an FP7 European Commission project that provides access to vessels and equipment to research institutes that don't have this equipment in their own countries.
The CUMECS expedition explored the Malta Escarpment using state-of-the-art technology on board the research vessel Urania, a 61-metre long research vessel operated by the National Research Council of Italy. The CUMECS team consists of 13 scientists and students from 8 different research and academic institutions. Their tasks on board the research vessel Urania comprised seafloor mapping and sampling and acquisition of video imagery of the seafloor and its habitats.
My role in this cruise is to coordinate all these activities, and in particular, I am in charge of the multi-beam echo sounder mapping. A multi-beam echo sounder operates by generating an acoustic signal from below the ship towards the seafloor. And we can measure the amount of time it takes for this sound to reach the seafloor and come back to the source. And by measuring that time, we are able to then estimate the distance, and by doing that over a large area, we can produce a 3-dimensional map of the seafloor in very high detail.
Now, the bathymetry system shows us exactly the model of the seafloor, but the advantage that we can also do is we can actually have a look at the response of the seafloor to the sonar to give us an understanding of what the seafloor is made of. What we call backscatter is the thing that we can really get an understanding for the seafloor type. And we can also look at that And we have this grayscale here image, again in a map configuration, and we can see the different types of seafloor. The brighter the seafloor is, the harder the actual seafloor is. So we can possibly say that the white areas here are rock, and the much darker area are probably much finer muds and sands.
So in CUMECS, what we're doing is we do first the seafloor coverage with the multi-beam, and then I come in with gravity coring. There's other ways of coring, and I sample what's below the seafloor. That helps me see what type of sediment there is there, and I can also use techniques to date them, like carbon-14 or other isotopes. It helps if there's any shells in there, because this is the material that we prefer to date, and it's the most reliable. The way gravity coring works is, on this ship, we have a trigger weight that hangs below the main corer, and this is the first thing that comes in contact with the seafloor. On the top, the weight has a cable. It connects to the head of the main corer. So when that comes in contact with the seafloor, it releases a cable that is rolled up on the top. So it allows the corer that weighs about a ton or maybe 2 tons, depending on what water depth we are, it allows it to have a free fall. And this free fall helps the corer go deep into the sediment. The deeper it goes, the better it is for us, because the longer record of sediments we're going to have. In this cruise, we've been working with a 6-meter barrel, but you can attach different barrels and make your corer longer and longer.
On the CUMECS cruise, we use the ROV, also known as the remotely operated vehicle, to study the seabed. Many of the discoveries in the deep ocean over the last 10 years or so, or even longer ago, have been made on the back of technological developments. And the same is true for the remotely operated vehicle. Basically, this is a robot which we can use to study the deep sea. It contains one or more video cameras, it can contain stills cameras, it has often one or more robotic arms with which we can sample items from the seafloor, or which we can use for carrying out experiments on the seabed. And it can carry any other sensor that we want to use close to the seabed or in midwater, such as temperature sensor, salinity, or anything else that can be useful. And so on the CUMECS cruise, we use this ROV, or remotely operated vehicle, or this robot, to mainly look at the different habitats that we have mapped before with the multi-beam system. So we will carry out video surveys, we will look at which animals occur in what kind of environment, we will identify different types of sediment, different types of seabed, or if it's steep or if it's soft sediment, or anything like that.
I've come from New Zealand, which is almost completely on the other side of the world, and there I work for a marine geology institute, and I study submarine landslides and canyon systems, as well as active tectonics which cause earthquakes in the undersea environment. I work with geophysical data to image the sediment below the seafloor. We have a seismic system that uses a sonar pulse to reflect off layers in the sediment underneath the seabed. We can look up to 200 meters below the seafloor using this equipment, and we can collect continuous lines that become like a fence profile of what the sediment looks like.
Using these various techniques, the CUMECS team managed to understand what the shallower part of the Malta Escarpment looks like. Seafloor erosion is a prominent process, resulting in the formation of numerous gully systems and channels across the Malta Escarpment. The longest channel is 12 kilometres long and follows the strike of a fault buried underneath. The seismic reflection data show that the shallower part of this channel has been buried by so-called background sediments, which are sediments falling out of suspension through the water column, whereas its flanks bear evidence of sediment deposition by bottom ocean currents. In such a dynamic landscape, marine life has still managed to find sites to inhabit and flourish. The ROV dives, for example, have revealed that many rock outcrops are colonised by sponges, hydroids and deep water corals. The most prevalent coral species recorded include black coral, desmophyllum and dendrophilia, which are located at depths of up to 350 metres. But perhaps the most striking discovery was the widespread occurrence of numerous submarine landslides of varying shapes and dimensions.
We have many layers of sediment, and some of them are moving downslope as landslides. Some of these are very large, many thousands of football fields in area, and they all join into a canyon system down onto the lower part of the Malta Escarpment.
They are fantastic processes. They can remobilize thousands of cubic kilometers of seafloor, which can be very dramatic, and if it happens as one event, it can wipe out every living thing on the seafloor. But the danger for us is that if we have any installations like cables or oil rigs or jetties or quays, those will be completely destroyed. So we need to know what causes them and what frequency they happen, and if we can predict when the next one will be, then we could probably avoid putting our installations there.
Collection of data during the CUMECS expedition is just the first stage of this project. Once the cruise is over, the CUMECS team will analyse the data acquired in detail. The multi-beam bathymetry and backscatter data will be used to produce morphological and geological maps of more than 400 square kilometres of seafloor. The 120 kilometres of seismic reflection data will provide information about the structure and stratigraphy of the seafloor and allow the CUMECS team to map faults, buried channels and landslides. 9 gravity cores will be investigated using advanced core logging technology to understand the recent activity of the canyon and determine the nature and age of submarine landslides. The video footage from the ROV dives, on the other hand, will allow identification of small-scale seafloor processes, benthic habitats and biota, as well as how these are affected by seafloor processes. Scientific investigation was not the sole objective of the CUMECS expedition. The expedition was also aimed at training young geoscientists who comprised half of the CUMECS team. The PhD students were trained in the operation of state-of-the-art scientific equipment, data processing and analyses, and dissemination of cruise results.
So this type of cruise is very good for me. I've only ever worked in Irish waters, so it's nice to come to the Mediterranean and see some sunshine and some calm weather. It's also good to meet people from other countries, other scientists, because these are connections that I will hopefully have for the rest of my career as a scientist. On board at the minute, we're working in 4-hour shifts. So one of my shifts is from 4 a.m. to 8 a.m. and then 4 p.m. to 8 p.m. So you have to get up out of bed and be ready to work at all hours. Part of what we were doing as well is running a blog online, which is important to make our science more accessible to the wider public.
Like Will, all the scientists in the CUMECS team started out as students who participated in numerous research cruises during their university degrees. Eventually, they acquired enough experience and expertise to lead and undertake their own projects. But what has drawn the members of the CUMECS team to marine geosciences?
So the perks of working as a marine geologist is that you meet a lot of people. On this cruise, I think we have 8 or 9 nationalities. I don't think there are many places where you can have something like that. And in the end, we all become friends, and somehow we end up collaborating again and again. We meet in conferences. And so that's the other great thing about it, is we travel a lot and we have a very good excuse for doing so. But marine geology itself is very exciting. Like discovering what's under the sea is amazing. Like going to a new place for the first time where no one's been before, that's real exploration. We do it in outer space, but we don't do it on our own planet. I mean, taking several different instruments and putting a story together, we are some sort of storytellers as well.
When recently a big project finished, the Census of Marine Life, people had discovered thousands and thousands of new species in the deep ocean over the last 5 years or so. And we know that there are still so many animals out there, so many environments we haven't seen before, so many environments we don't understand. So I think the job we have to go and study this in a kind of holistic manner, in a way that several disciplines are together, is a really interesting job, and I really like it.
So to become a marine geologist, I studied for many years at university and have done a PhD. And the reason I put so much time into this is because it's just a very exciting job. The interest of discovering new things in the underwater environment keeps you enthusiastic and excited. And we have beautiful days like this to be out at sea. Of course, it's not always so nice, but really you get to experience a lot of amazing things, travel around the world and see some great places. And the aspect of discovery is enormous. We know much more about many of our planets and the moon than we know about the undersea environment. And so in places like where we are mapping right now in the Malta Escarpment, nobody has ever mapped the seafloor here before. Everything we know is from very remote and very coarse understanding of what the seabed looks like. But now we can go down and in detail we can understand the form of the seabed, and with the seismic data we can look right into the sediment and understand over very long periods of time, and we're talking tens of thousands to hundreds of thousands to millions of years, how the seafloor has evolved, sediment coming in, sediment eroding away, and biological communities developing in the landscape.
The CUMECS expedition is only the first stage in what is hoped to be a long scientific collaboration between the team scientists, students and their research institutions. The EU-funded project Eurofleets was instrumental in providing the funding and equipment to bring the team together and carry out the expedition. The majority of the Malta Escarpment remains unexplored, however, and the CUMECS team will continue working hard to reveal its secrets.